The phenomenon we just observed with the nonlinear systems, the sensitivity to initial conditions, the sensitivity to changes in the modeling parameters, presents us with a problem if we actually want to use our model to forecast anything. We only can be so precise in knowing what our initial conditions are or knowing what our parameters are of the model. So again, thinking of this, for example, in the weather context, we can only measure our current temperature with so much precision based on the instruments that we have. But we see that if we're off by even a tiny, tiny bit, the forecast that we make can be way off from the reality. So what we want to see now is, how do we deal with this? How do we still make use of these nonlinear models to make a forecast and to make predictions that are worth anything? So what we're going to try to be doing is estimating under uncertainty. So if we can quantify the uncertainty in all of these inputs, the modeling parameters, the initial conditions, we're going to be able to quantify the error or the probability of what our outputs are going to look like. So what this is going to let us do is say, in our estimates, in our forecasts, we're not going to be able to really say, okay, at 30 days out, the temperature is going to be exactly 35.4 degrees. But what we will be able to say is, with some like 95% certainty, the temperature is going to be between, let's say, 30 degrees and 45 degrees. And highly dependent on the system and dependent on the accuracy of our instruments up front, that range could be very narrow or it could be very large in what we can say. But we're not going to pinpoint an exact value, just a range of values that the forecast is going to have. And again, if we think about weather as our overlying example so far, that's exactly what we see. We're not necessarily told, yes, it's absolutely going to rain or not. We're given a probability of rain happening, and that's tied to this sort of uncertainty. We're also not told the exact temperature at certain times of day or for the day. We're giving a range of what temperatures we can expect to see during a day. And in a little bit broader sense, we don't know necessarily the exact path, let's say, a hurricane is going to take, but we're given some band of certainty that we think the hurricane is going to take as it progresses through time. Now, one way we can develop these estimates is using Monte Carlo simulation. So really what we're going to do here is we're going to run our simulation, run our model thousands, millions, tens of millions of times, depending. But each time we run it, we're going to give it a slightly different either initial conditions and or modeling parameters. And what we're going to do is give it some random value in that range of uncertainty we think we have for the initial conditions or the parameters. So what we're simulating is kind of thousands, millions of these parallel universes where we have a slightly different measurement taken, a slightly different value for our parameter. And for each one of these, we run it through our model, and then we record our results. So we can see under these exact conditions, what would our estimate of the temperature be 20 days out, 30 days out, 50 days out? Okay, let's run it again under slightly different initial conditions and do the same thing. So we give it thousands or millions of different inputs, we run our model, and we get thousands or millions of different outputs. And what we're going to be able to do is map, for a given input distribution, what does the output distribution look like for our system? And this gives us this probability range that we're going to be seeing for our estimates. And usually what's going to be the case is the more simulations we run, the better our estimate is going to be. We might be able to get a little bit tighter of a range of the probability of our estimates, and the precision of them is also going to generally go up. So let's see how we can implement it for this Lorenz system in our example. All right, so what we're going to be doing in our example is developing a PDF or a probability density function for our X value when we forecast 30 days out. Now I could have done this 20 days out, 50 days out. I could have looked at the Y or the Z. I can do all of these things. I just want it to be simple enough for the moment. We're just going to look at the value of X. If this has been our temperature or pretending it's our temperature, we're going to stick with that. So what is our temperature going to be 30 days out according to our model? But now we're going to allow for the fact that we have some uncertainty in what the temperature right now is. So I'm going to run it with those same parameters we've been using. And what I'm going to do is I'm going to run, in this example, 100,000 simulations. So I'm going to pre-allocate here my temperature estimate at 30 days out. And I'm going to make 100,000 different estimates based on 100,000 different, slightly different initial conditions. All right, so I'm just pre-allocating the size here. We're going to see in the loop how I'm going to fill this out. All right, so I am going to say, for this example, I have 100% certainty that my initial y value is 0, my initial z value is 1, but I have a little bit of uncertainty as to what my x value is. So I'm using that same scale that I used before. So each time I'm going to have a number close to 1, but in this normal distribution around 1. So if whatever instrument we are using, we can quantify to say, all right, it's going to have the temperature that we read is coming from a normal distribution around the true value with a standard deviation. Here I'm putting in 1 times 10 to the negative 4. So that is pretty small. That is pretty precise. The value that we measure is going to be close to, but not exactly the true measurement. That's what this is simulating, is if the true value were 1, what we measure is going to be a little bit lower or a little bit higher. But when we measure it, we don't actually know the true value. So we're going to run this, we're going to put it through the ODE solver, and we're going to get our solutions for that particular initial condition. Right? And what I'm going to save out of that is, at the end from that run, this x11, that is telling me what was the initial value of x. I'm saving that to this vector x0. And I want to save what's the final value of, again, I'm just looking at x in this case. So the last value of x, so that first column of the output here, I'm going to save into the vector x30. And then I'm going to repeat this. I'm doing it in a for loop. I'm doing it 100,000 times in this example. I'm going to keep simulating it for a slightly different initial condition, recording my initial condition, recording the value at 30. We're going to see later that we can do this for more than just 30 days out. But for here, I just want to focus in on what's my estimate at 30. All right, and then we're going to see at the end, once our simulation runs, the distribution we had on our input or inputs. We're only looking at one variation right now, and then how that maps to our estimates 30 days out in this example. So let me run this, and we're going to see how the uncertainty in our input is going to relate to the uncertainty in our output. So these are the histograms that are produced. Running this code can take a while, as we have to keep rerunning this, in this case 100,000 times. It would take maybe 10 times as long if I wanted to do it 1,000,000 times. We'll see in a moment how many times we really need to run it. On the left here is the histogram of the inputs. So this is the value of x at time equals 0. So notice that the average is at 1, and our standard deviation by design was 1 times 10 to the negative 4th, and I do check that in the code, which I'll get back to in a second. All right, so very, very close to 1 in our simulations. What the histogram is showing us, this is a normalized frequency histogram. So the y-axis is showing us the ratio of the runs that were in these little bins. So how many times was the value of x between 1 and 1.00001 or something like that? Well, that happened about 4% of the time. So this is just a visualization of the value that x took, for the initial value that x took. And then on the other side, after I run all of these initial values through the model, and here I just chose 30 seconds to be the point I wanted to study, what is the value of x out of the model at 30 seconds when I turn that crank and push time forward? Do notice the scale of the x is much different at 30 seconds than 0 seconds. So 30 seconds, we see that on average about the value of x, or the temperature estimate, let's say, is 0. However, the range is really big. We see that the range is going from like -20 to 20, and it's no longer a normal distribution, and we shouldn't necessarily expect it to be either. But we can still get a sense of how big is this spread of values. So in the code, I am having the code look at the mean and the standard deviation, or the amount of spread of the initial value of x and the value of x at 30 seconds. So that's what these values are here. So by design, we saw that initially the mean was 1 and the standard deviation was 1 times 10 to the negative fourth, and we're very close to that. But then after 30 seconds, we're seeing our average is close to 0. That's what, I'll just rerun this. We see that the average is pretty close to 0, but the mean, the standard deviation, is 7. So we're seeing a lot more spread at 30 seconds than we saw initially. Again, this is coming into play, the sensitivity to initial conditions. Even though they were all relatively very close to each other, the spread was relatively very small. After 30 seconds, that spread of values got very large. But it at least is quantifying what we can expect the value to be. If we know that our initial measurement was somewhere in the realm of 1 with this little bit of uncertainty, now we can quantify how uncertain we are at the result after 30 seconds. All right, we'll get a little bit more in depth in a moment, but how do we know we ran enough simulations? So I said 100,000. I seem to take that out of thin air. What we always want to look at when we're doing a Monte Carlo simulation and many other numerical simulations is, has our solution converged? So that's what this third plot is going to be showing here, is the convergence plot. Right, so the x-axis is showing in log scale how many simulations I'm running. Right, so when I run only 1 or 10 or 100, 1,000, etc., up to 100,000, that is what n is showing. And then my y scale, what I'm doing here is basically taking the running average of the value of x at 30 steps ahead, at 30 days. Right, and there's other things we could be measuring here to see if we converged. This is a pretty common one. So for example, after I run one simulation, I take the average of that one simulation, well, that's just going to be the value, and I plot it. Now I run it the first 10 simulations. What I'm doing is taking the average of those first 10, and that's what value I'm putting on here. Then I go for 11, 12, 13, etc. I'll just jump to, after 100 simulations, I take the average of those 100 values of x at 30, and that's what I'm plotting here. So we can call this kind of the running average or the running mean as we keep adding more and more simulations. So we see that the average is changing a lot for the first 100, even the first 1,000 simulations. It keeps kind of fluctuating. But then if we get to about, let's say, 10,000 simulations, this line is more or less flat. And what that is telling us is that as we are adding more and more simulations after about 10,000, the values we're getting are not really significantly changing the mean anymore. That mean has really flattened out. And that, at least visually, is what we're looking for to show that, yes, we've run enough simulations that we can trust the results. They're precise. More simulations will almost always give us more and more precision, but it's not going to add much more precision, because to get a little bit more precision, we might have to dectuple the number of samples, the number of times we're running our simulation. And we really get diminishing returns where we're barely going to be improving the precision anymore, but we're running 10 times as many simulations. What we wouldn't want to do is be at, let's say we only ran this 1,000 times. Well, this line has not flattened out yet, so that is an indication that we probably should be running more simulations before we can trust the data. And we're going to be seeing convergence in the future as well, but we want that flat line, and it is a judgment call. What does flat really mean? But once we see that line flatten out, then if we ran this 1,000,000 times versus 100,000 times, once we reach this flat area, really our results are not going to change very much. All right, so we know that 100,000 times appears to be enough times to be running this. Let's expand out a little bit what we're looking at, because here, just for the demonstration, I'm using only 30 days out. I want to see what my estimate looks like over time. So I'm going to look at, again, just the value of x, but instead of just this snapshot at 30 days, I'm going to see what's my estimate over the first 45 days. And we'll see what we just saw, but from a slightly different perspective. I'm going to keep taking these snapshots between 0 days and 45 days, but I'm not going to be looking at that full probability density function. What I'm going to be looking at is what is the 2.5 percentile. So that is what number is 2.5% of my data lower than that number. And I want to look at the 97.5th percentile. So I'm finding what value is 97.5% of my data lower than that number. The difference between those is a range of 95%. So basically I'm trying to find that middle range where 95% of my estimates lie in that range. So I'm cutting off like the extreme left tail and the extreme right tail. So I'm saying is with 95% confidence, the value of x is going to be between this lower bound and upper bound. All right, so let's see what I'm doing in the code. Really the setup is exactly the same, but now I'm saving all of the information from 0 to 45 for every run. And what I'm going to be doing is plotting for all 100,000 runs at every time step what is the 2.5 percentile and the 97.5 percentile. That's what 164 and 165 is doing. So the area between those lines is going to show that 95% of the time, that's where my value of x was as I go through time. So I'm going to run this, and then we're going to see visually what's happening. So this is the chart that emerges. The blue line is that 2.5 percentile, and the red is the 97.5 percentile. And again, I'm just looking at the value of x as time goes forward. All right, so we're starting here, a value of 1. Well, all of the simulations are starting very, very close to 1. And we see that the blue and the red line are basically on top of each other for the first 17 seconds or so. Thinking back to that phase space simulation we did with just those 4 starting points, this makes sense because they were all bundled together for that first 17 seconds or so before they started to diverge. So our confidence, our 95% confidence interval is very, very tight here. We know with very good, very narrow certainty the value that x is going to have, no matter what our start point is, close to 1. No matter what the start point is, we can say with a lot of certainty that we have this very narrow field for the first 17 seconds. But now we see that that 95 and the 2.5 start to separate as we go forward. So they're close, pretty close together until about 20 seconds, and now they're pretty far apart. So once we get past 25, 30 seconds, this is now our 95% confidence interval, where it was basically on top of each other over here. It's very wide here. So over here, I can say with 95 that the value of x at 13.5 seconds is going to be negative 1.6. I can say that fairly definitively. However, coming over here, let's say at 35 seconds, I can say, well, there's a 95% chance that x is at most 14.56, and at the smallest, negative 14.96. So this whole range is now my uncertainty on x. Now, I want to point out this system is a pretty extreme case of this divergence happening. Not all nonlinear systems act this way, but my uncertainty over here is really big, at least at 95%, compared to the first 17 seconds where it's really, really tight. So if this is indeed my inaccuracy of the initial condition on x, this represents, as x goes forward for 45 days or t equals 45, where I can expect that value of x to be as I move forward in the future. So at least I can make some estimate as to the value of x. It's just a pretty wide band. I can say, well, it's likely to be between negative 15 and 15, but I really can't say much more about that. Now let's contrast this back to the linear system that we were looking at earlier. All right, so I'm going to do the same thing on that linear system, and I'm going to be even more extreme a little bit in the uncertainty I have in my initial conditions. Actually here, I'm going to put uncertainty on my parameters and on my initial conditions. So my parameters are going to change, all three of them. This is back to the linear system, the k, the b, the m. I'm going to change those. K of 3 plus or minus a little bit, b and m of 1 plus or minus a little bit. And then my initial conditions are going to be 1 plus or minus a little bit, and then 0 plus or minus a little bit. So this number is just going to be a little bit bigger, a little bit smaller than 0. So in this linear case, do note that I'm using 10 times 10 to the negative 3. So the spread is more than we just saw, and the spread is on both initial conditions and all three parameters. So let's see what this looks like from the histogram perspective. I am going to do this for 60 seconds of simulation. All right, so these are the histograms that come out for the linear system, the spring mass damper. So again, on the left, even though I am putting slightly different initial conditions on x and x dot, as well as the k, the b, the m, I'm only going to show the x for this. We see that it is a mean of 1 and a standard deviation of 1 times 10 to the negative 3, just as we designed. And now we're seeing what's the value of the position 60 seconds out. Here I think it's labeled 30, but this was really 60 seconds. So it has this kind of weird shape here. Notice the difference in scales here. This is times 10 to the negative 7, and this is just times 1. So the position, once we have gone through our simulation and we've gone 60 seconds, our average is very close to 0. The mean is close to 0. If we look down here, negative 2 times 10 to the negative 7, really small. And also the spread is very small, 3.3, but that's times 10 to the negative 7. So the difference in scale kind of exaggerates it, but pretty much after 60 seconds, all of those initial conditions varying the position, the velocity, the k, the b, the m, they all end up extremely close to 0 in their position. Now we do have 6 things that we're changing in this Monte Carlo simulation. So generally, the more things that you're letting vary, the more simulations you have to run. So if we look here, I probably should have run this maybe a little bit more. It's not quite as flat as I would like to see it, but I think it still gets the point across. This linear system is certainly acting different than the nonlinear system, the Lorentz system that we're looking at. Even though we're getting here, the output distribution is actually much tighter than the input distribution. The opposite was true in the Lorentz system. If we continue through, let's look at those confidence bands, the 97.5 and the 2.5 for the linear system. So I'm going to run this for just 20 seconds here, but same idea as for the Lorentz system. I want to know, how does my uncertainty or my confidence interval change over time in the simulation, but now for the spring mass damper system. Again, I'm going to be even more variable than I was for the Lorentz. I'm letting the KBM change around every time, and my initial conditions change every time. And we're going to see, just by tracking the position, what can we expect. All right, so taking a look at the results here, we can barely see even a difference between the lower bound and the upper bound. This 95% confidence interval in this linear system, extremely tight. So we see the position over time, even with varying all 3 parameters and 2 initial conditions, still 95% confidence interval is very, very small as we go forward 20 seconds in this system. Doesn't look at all like what we saw for the Lorentz system, where we have a lot of uncertainty. We have very tight certainty in the position of our system, even under this uncertainty in our inputs. All right, so bringing it to a discussion for this subsection on estimating under uncertainty with our input parameters and our modeling parameters. With enough simulations, we were able to create a probability density or probability distribution of our output at specific times or over time ranges for our nonlinear system, and we did for the linear system as well. And what this is able to capture is this confidence interval of the value of our state or states over time. Again, we can't really say what the exact value of our state is going to be 30, 45, 60 time units out, but we can at least establish this 95 or 97% confidence interval that we're interested in. And we're able to bound, well, what's the lower and the upper bound we should expect on the value of our state. All right, so we have to be aware that when we are making the model, it comes with some assumptions and simplifications, but we also need to be aware that we have finite precision and a little bit of uncertainty in what our initial conditions are and what the parameters were in our model. Now, we saw by example, once again, for that linear spring mass damper system, the uncertainty to some degree doesn't matter too much on our initial conditions or the parameters, even if we have some uncertainty range in those. The results are more or less going to be the same every time we run it. That was not true in the nonlinear system. We saw even a very small difference in one initial condition had huge impact in what the confidence interval looked like as we simulated our system and pushed time forward. And again, if we think about spring mass damper system versus other real-life nonlinear systems, sticking with weather now, the uncertainty of measuring all of these atmospheric conditions now means that as we go forward in time, 1 day, 3 days, 10 days, the further out we go in time, typically the less certainty we have on what those future conditions are going to be. And little problems with the measuring our modeling parameters are going to impact it as well and increase that uncertainty as time is going forward. And I want to reiterate that this system we're looking at based on its parameters and how it's set up is, I have in quotes, highly chaotic. That's not necessarily a good phrase or not, but doesn't necessarily represent typical nonlinear systems. Not all nonlinear systems are going to have this wide confidence interval as we push forward, but typically they will have much more uncertainty of our outputs than linear systems are going to have.